So I'm Hasham, Senior Data Scientist at Johnson Labs, and today we'll be going over delivering state-of-the-art accuracy for healthcare NLP. First, we'll start with what actually is Spark NLP, and how do we establish when we say delivering state-of-the-art accuracy, because it's both backed by academic research as well as some of the benchmarks that anybody can run. The code is out there. It's pretty reproducible. Now, Spark NLP for healthcare actually is based on Spark NLP. What is Spark NLP? It's an open source project initiated by Johnson Labs. And now it supports more than 300 languages. It has approximately more than 5,000 different pre-trained models. It's basically an NLP solution. It's open source, so anybody can go look to GitHub, look at it, look at the code, extend, add new functionality, provide support. So for example, we have support for different languages, Python, Java, Scala, but open source community contributed to us for R as well. Yeah, that's open source contribution. Now, Spark NLP for healthcare is built on top of Spark NLP. What I mean by that is, and the focus of Spark NLP for healthcare, as the name suggests, is basically add more functionality that is very specific to healthcare. What do we mean by that? First, let's skip accuracy because that's what we'll be dealing with. The next thing is scalable. As the name suggests, Spark. So it's the only library out there that is natively extended by core Spark ML classes. So that means you have a Spark cluster, you fire up Databricks, you have AWS EMR, anything for that matter. The code would just run. You don't need to configure your cluster. If you already have it configured, that's good. But you don't need to do any other changes. So you have your cluster, either cloud platform or your own. You just run the code. It would run. And being Spark, you can naturally scale it up to, if you want millions of records, billions of records. It's up to you. How well can you scale your cluster? Private. Now, what does that mean? In healthcare, everybody knows that we have a restriction of high compliance when it comes to HIPAA, PHI data, all of that. So when we say private, it literally runs on your own infrastructure. Unlike an API, it's not just an API, it's rather a framework. So you don't need to send anything. All you need to do is, it can download models from our models hub on S3 and other stuff, but once it's there on your environment, it never connects to anything outside. It leverages your infrastructure, your compute resources, and everything. So that's private. Tunable. Now, actually we've seen a lot that people would say that we want turnkey solutions, but tunable is really important because a lot of customers or a lot of companies actually have their own custom taxonomies and ontologies. A company that is very specific to, let's say, oncology, they would define their own systems. So that helps us appeal or fulfill use cases for those customers. When we say tunable, all you need, as we've already seen, that you don't need too much data. You can literally fine-tune or train your own models that would do very well on your data distribution, like 500 examples, and that's tunable. It's pretty easy to do that as well. And then modular. The code base itself is more like a jigsaw puzzle. Inputs or outputs of one component goes into second. For example, you start with a very basic problem, a classification, then you realize, no, there are spelling mistakes in my data, it's noisy. You just add in a new component that's called spell checker. It would correct it for you. You see any other mistake for that matter, or stop words, you just add in a new component, it would do that. So it's modular, it's like piecing puzzles together. One output of one module would go into next, and then this is how you do it. So it's modular. Now, the capabilities are, some of the basic capabilities are already listed, like stoppers, etc. That's not the main thing. The main thing is actually named entity recognition, because in clinical terminologies, the main core chunk actually comes from the named entity recognition models. You have large pieces of text. You say, I want to extract, let's say, HCC risk adjustment codes. In the large piece of text, you would first want to identify where to look for that piece of code, where to map that piece of code in there. So first you need to identify named entities. So that's the core thing, and it's explained here. Those entities are then fed into a bunch of tasks. First, like I said, resolvers, clinical entity linking. You want to extract or you want to link, you want to extract ICD-O codes. You would first run NER models that is very specific for oncology. You would run an oncology model that contains codes for ICD-O mapping. You would get ICD-O codes. Same thing you can do with CPT. At the same time, if you want SNOMED codes, RX norm codes for drugs, it really depends. Now, assertion status, what does that mean? So, for example, you want to identify or see if there's a family history of any particular disease. Now, again, those concepts would first be identified by the named entity recognition model, and on top of that, this layer would tell you, okay, this is something that happened in the past, or it is a procedure that has been recommended for the future, or if it's related to family. So things like these, then you can segregate and do better analysis, or basically build up your database. Then de-identification, a really common use case. In reality, in unstructured text, de-identification runs purely on these named entities. You want to extract patient's name, named entity recognition. You want to extract age, named entity recognition, address, anything for that matter. Then there's a component, de-identification, that deals with that. And for example, if it's age, we would normalize it. We would say plus minus 40 days, according to HIPAA. Either redact it or replace it with a good random value. Names, males' names would get replaced with male names. Female names would get replaced with female names. And not only that, we also have built a sort of a structure or a mechanism so that John always gets de-identified to John. You'd maintain the data integrity in there. So that is de-identification. And then relation extraction. For example, a person took 2 drugs, and one of the drugs gave that person, let's say, headache. Now, the relation extraction model would come into play here and say, okay, one very specific drug was responsible for an adverse event, not the other one. So, but all of these things that you can see is fed by the named entity recognition model. And naturally, what that means is any error at this stage gets trickled down into the later stages. So bringing it all together, if you look at a piece of text like this is what happens. When you run named entity recognition, assertions, resolver models, you would see you will be able to identify age, type 2 diabetes, UMLS codes for that, SNOMED. As we can see, assertion is past because it's a history, and then relative ages, and then you can link all of these together. As well as more granularity in terms of drug, like drug name, dosage, frequency, how to take, administration instructions, all of that. This is all named entity recognition, and then we build either relations or assertion on top. Now that we've established what Spark NLP for healthcare and the capabilities are, how does it compare to other solutions out there? So there are a bunch of them, but mostly we'll be going after or comparing ourselves with the big cloud providers, AWS Medical Comprehend, Azure, text analytics for healthcare, I think, and Google Cloud Healthcare API. The main thing is that it's really hard because they don't release any benchmarks, any white papers, any data, so it's really hard to compare apples to apples. What do they have in their database? What are their models trained on? But for the sake of, to get as close as possible, what we have done is basically we'll be comparing it with some open source data sets out there that would be like taken from empty samples, in which we sample 8,000 sentences randomly. We would run it through our models and their models, and not only that, we'll be training our models only on this data set just to get a fair comparison, so we don't have any data overlaps. But before that, because I've already mentioned that we have so much granularity, and all of this can be seen here. You have got models very specifically specific for biomarkers, oncology, nephrology, anatomy, protein, genes, and we've got different model architectures as well based on your needs. For example, if it is you want more performance, go with the BERT model. You want more scalability, you can compromise a bit. Your data is not too noisy, go with the standard BILSTM architecture. That's pretty nifty, pretty simple, and pretty fast, but pretty accurate. So that's that. Now, comparing the capabilities compared to all the other cloud providers, so as you can see that GCP, Azure, and AWS, they've generalized entities. But as I already explained that we have more granularity. So you just don't get an entity like problem, rather you get, okay, it's a problem that's related to, let's say, diabetes, obesity, oncology, things like these. Similarly for test, if it's not just if it's a lab test, or is it an imaging test? What's the result? Oxygen therapy, WBC results, things like this, so more granularity. Naturally, since we have more granularity, when we compare with the cloud providers, we will bring them down into one umbrella for a fair comparison. This is just a demonstration of, we support now more than 400 entities powered by more than 100 NER models. So yeah. Now, I'll go back, yeah. Okay, so now comparing the results. As I've already explained, the way we establish these results is we sample 8,000 nodes from emptysamples.com. Anybody can do that. It's an open source database. And then we basically train, so we retrain our models and we compare it with the cloud providers just to make sure that our models does not contain that data, although they would contain other data sources, but not that. As we can see in the benchmarks, the test entities were better. Treatment, medication, anatomy, condition. In anatomy, it's a big difference. But in general, we are a lot better compared to Azure. The reason for that is, the primary reason for that is, since there's a recent trend towards building large language models, and then you using zero-shot learning, so you don't need training data when you're actually fine-tuning, we have enriched our database a lot. And our language models, be it BERT, be it Glove, are a lot more enriched because we've done that over years now. So we're better when it comes to these core entities. Compared to AWS, again, the test result is roughly more than 10% better. Treatment is better. All the results, these are all named entity recognition, that's to note here. All the named entity recognition results are better. The metrics are better. Compared to Google Cloud, again, we're better for condition. Now, you would see that sometimes this would change, the entity types at the bottom. The reason for that is it really depends which cloud provider are we comparing against, because not all cloud providers support all types of entities. So that's that. Putting it all together, you can see that taking all of them, all the common entities into picture, AWS actually does quite better, and Azure as well, but we are actually better in nearly all classes when it comes to named entity recognition. Now, again, the question might be that we might have some overlapping data, but two answers for that. One, it's good for the customer. Second, we don't know what the data these cloud providers have, so we cannot say anything for that matter. But a more elaborate answer is actually a few slides back, and that is this. So this is our results, what we tested on empty samples. But what about comparing it on standard data sets? So we really compare, we really go for state-of-the-art accuracy out there and compare our models, our language models and architectures. And even in that case, we can see that on standard training, validation, testing data sets, we're better for all the I2B2 data sets, all the other biomedical data sets, NCBI, BC5. Code is out there, it's reproducible, and even address drug events. So we're better in terms of NER. Now, bringing that NER concept to de-identification, we have support of 5 or 6 different languages. But for now, we're only going for English because that's what we can compare against. In the case of de-identification as well, as you can see that the recall or the FN score of all the entities is pretty high. We support more than 20 different, close to 17 different types of entities out there. And compared with SOTA, it's pretty easy. You just compare it with the 2014 I2B2 dataset. We can see that we're better in terms of the overall macro F1 is better than the SOTA by 3%. Similarly, compared to cloud providers, in the case of if we drill down to entity types, we're comparing different languages, we're still better. Compared to cloud providers now, again, we're better in the sense we are roughly 100% in the case of age, date, doctor, all of these things. So de-identification benchmarks are better compared to cloud providers. And these are actually standard data sets. This is not something we curated. These are standard data sets. Anybody can go out there and check. Now, entity resolution benchmarks. This is actually assigning codes to concepts, ICD codes, CBD codes, SNOMED codes. In this case, you would see when it comes to RX norm, AWS is second best, and Spark NLP is the better one. Now, in the case of SNOMED, yeah, this is the one where we're still just a tad behind AWS, and the reason for that is the SNOMED vocabulary is way too large. So yeah, but it's pretty comparable. I mean, the difference is what, like 1%? In the previous case, we are already better by, in some cases, by 9%. So in SNOMED, these are the results. For ICD-10, again, we're better. Now ICD-10, because ICD codes have a structure, we can go for more general, we can take only the first 3 or 4 terms and being less specific. Again, we're better compared to GCP and AWS and other cloud providers. We said in 94, the others at 87, 61, and 63. And these are the results. So top 5, what does that mean? Based on the predictions, the top 5 terms we take, and then we compare overlap. It's not just one prediction. So in that case, we're, again, better compared to all the other cloud providers. So yeah, that's pretty much it. This is what establishing state-of-the-art really means. And any questions, happy to answer. Thank you.